It's time for another British Science Week interview with UMPO, and today Annabella is chatting to someone who studies the biggest possible questions, and we think that's pretty cool.
Hi, my name is Annabella. I'm a third-year undergraduate physics student at the University of Manchester, and I'm also the Events Manager for UMPO, and today I'm here with
Professor Scott Kay, and I'm a Professor of Cosmology, well, specifically astrophysics, in the George Bank Centre for Astrophysics, part of the Department of Physics and Astronomy.
Amazing, cool. Great that you're here with us today. Could you give us a short definition or otherwise phrased a summary of what cosmology actually is, like an introduction into it?
Yeah, cosmology is actually a study of our universe as a whole. So it sounds very big and very grand, but it's actually what we want to understand on the very largest scales in the universe. So we obviously, the universe is full of very complicated things like stars and planets and life, but we want to try and understand how the properties of, for example, galaxies and clusters of galaxies behave, and how they form in our universe. So we're really trying to ask some of the most fundamental questions in science, really.
That sounds genuinely amazing. What do you personally do as a cosmologist, like as a researcher? Like what do you actually do?
Yeah, so that's a good question. So there are sort of different types of cosmologists. There's what we call observational cosmologists, and what they do is they gather data using the latest telescopes, and they perform very large surveys. So they look for, lots and lots of galaxies, and they map them out. And then there's what we call theoretical cosmologists, who are the kind of scientists who like to sit down with a pen and paper and figure out what this all means. So they try to build physical models, if you like, or mathematical models that describe our universe and the observations. Now, I'm kind of in the middle. I'm what's called a computational cosmologist, which sounds a little bit kind of ordinary. We all use computers these days. But what we've realized is that these models that we're building, we have to actually use computers in order to include all the complicated physics that goes into understanding our universe. So what I do is I'm involved in projects where we run large computer simulations that model sort of regions of our universe, if you like, and we try our best to put in the physics that we know must be there, like gravity and stars forming, how gas has pressure, these kind of things, and we see if we can actually simulate a region of our universe that looks like the real universe.
Okay, really, really cool. So why should we care? Like, why do we care about being able to model the universe, galaxies moving and things like that? Why is it important?
Well, yeah, that's a very important question. I think, there are several reasons why we care. So one of them is rather kind of profound in that, cosmology is part of astronomy. We're all fascinated by what's around us, where we came from, what's out there and beyond our own planet, beyond our own solar system. So, I mean, that's really an astronomy, a reason why we like astronomy. And cosmology is essentially part of that. So, I find this amazing that we can look through telescopes or observe the universe through telescopes. And what we're actually seeing when we look at distant galaxies is the universe further back in time. So this amazing idea that we can look out into the sky and actually see what our universe was like before and build a picture up of how our universe changes. And that really gets at this kind of profound question: why are we here? And what is our place in the universe? So I think that's really the kind of probably the most significant answer. I think also cosmology has a multitude of things that you can do if you learn doing cosmology. You're studying a fascinating subject, but you're learning lots of things about physics, about computer programming, and so there's all sorts of practical, things that benefits us from cosmology. But fundamentally, I think it really helps us to understand our place in the world, and the fact that Earth is such a small thing, a small object when you think of the universe as a whole.
Okay, amazing. Thank you. What is your particular area of research? Like, what are you currently focusing on? What are you doing?
Yeah, so my area is there's sort of two things that I'm really interested in. One is that I really like to understand whether our basic picture of the universe is correct, so what we call our standard cosmological model. And there are two really significant puzzles in that model. One is that we need lots of dark matter. So when we measure how fast galaxies are moving in the universe, we find that in order to explain those speeds of those galaxies, we need to have lots of matter there that's not visible, that's not emitting light, and we call this dark matter. Now, it turns out, fortunately, that this dark matter is easy to put into a computer in a model because it only responds to gravity. So, the same reason why things fall into the Earth, Newton's laws, also explains the motions of galaxies due to dark matter. So one of the things I'm really keen to do is to test using these simulations whether our understanding of the universe with this dark matter really actually agrees with the observations. The other puzzle is something called dark energy. And that's this idea that when we look at these galaxies that are moving away from us in the universe, they seem to be not only moving away, they're actually moving away at faster and faster rate, what we call cosmic acceleration. And mathematically, the only way we can really explain this is to have this mysterious thing called dark energy. And we have no idea what dark energy is. But again, we can put it into our mathematical models, and we can test this idea and see whether what we get out of our simulations really agrees with observations. And so those two puzzles we can really look at with simulations, and that's what I'm currently mainly interested in. The other side of it is I'm also interested in why or how galaxies form and how galaxies change with time. And so one of the nice things that we are doing at the moment is that we're building these models which include galaxies forming in our simulations. And so we're really getting to the stage now where we can actually make predictions for the different types of galaxies we see in the universe. So we see that galaxies have nice spiral features like our own Milky Way. And we also see different types of galaxies like elliptical galaxies. And our simulations are actually able to predict these different types of galaxies as well, which is really cool.
Okay, that's amazing. Coming back to the dark energy bit, here's a hypothetical question. Say you figure out, like you manage to set up a model that with the inclusion of the concept of dark energy quite accurately represents what we're actually observing. What would the next step be towards figuring out what dark energy is?
Yeah, so this is something that cosmologists, particularly observational cosmologists, are really interested in right now. So the next steps is testing the type of dark energy that we have in our universe. So even though we don't know what the dark energy is, we can make different models for how that dark energy behaves. And so the simplest model that we currently put into our simulations is called a cosmological constant. And that just means that the sort of density of this energy, if you like, the amount of this energy in a fixed volume is constant. It's just constant at all times, which is a really strange thing to have in physics. But it's a very simple mathematical idea. But there are other models that say, well, actually, this dark energy might not be constant. It might change with time. And so, again, we can put simple models into our simulations and our theory that actually allow this dark energy to change. The problem is that these different models produce very subtle effects. So if we want to observe whether dark energy is really a constant, it's not changing with time, or it's actually changing with time, then we really need to make very, very accurate observations and understand our observations very accurately. And so I think that is probably the next big step, is being able to use our observations of the universe and say, is dark energy really constant, or is it changing with time?
Okay, fascinating. Slightly more towards back towards you as you yourself. How did you get into this career of being a researcher in cosmology? Like, how did you get there?
So going back to when I was at school, or yeah, okay. So when I was at school, I realised, secondary school, I realised that physics was my favourite subject. I don't know really why, if it was my teacher or just the actual subject itself that started it, but I love physics, and but not really too much about astrophysics at that point, or cosmology at that point. And it wasn't until I was looking to apply to university and I knew I wanted to do physics, I realized there was this degree that you could do in astrophysics. And I thought, oh, astrophysics sounds really, really interesting. That means I can apply this physics to space. And so I applied and I did a degree in astrophysics. And when I was in, I think, the last year of that degree, I got to do a course on cosmology. And I learned that you actually knew something about the universe. And I thought, wow, that's really exciting. And at that time, I was quite lucky, actually, that when I was applying for PhDs, which was the kind of next step in the academic career, there was a group in the UK, in Durham, where I did my PhD, that was really into doing these simulations, these computer simulations of the universe. And it just happened to be at the time when I was applying that this came out in the news and things about these simulations. And so I applied to Durham and was lucky to get a PhD place there. So, and so from then on, I've just, developed my career, my research in cosmology, and I've just, it's been my favorite thing to do ever since.
That's great. Did you always think that you'd end up as being a researcher, or did you think, oh yeah, I'll do physics at uni and then I'll go and do some other job?
To be honest, I always wanted to do it. I think as time went on, I understood more and more what that meant. But I always loved doing physics. So for me, it was always try and have a career in physics for as long as I could. And I'm lucky that I've managed to stay in that career. Of course, there's lots of other careers that are really exciting that you can do, with a physics degree. But in my case, I was fortunate enough just to be able to continue doing physics.
That's great. What's your favorite part about being a researcher? Like, what do you enjoy the most?
Probably that initial stage where you first get some results out and you think, oh, that's interesting. So there's lots of parts of doing research where, just like everything else, you have to be disciplined. You have to you have to write reports. You have to give talks, and that's fine. They're all really interesting. But probably the most interesting, the most exciting thing is when you first are exploring data and you get these results, and I mean, something jumps out at you and you don't immediately understand it and you think, oh, that might be really interesting. That's probably the best part of doing research.
That's great. And then slightly differently, what's your favorite part of physics in general? Like, what's your favorite area of physics, like specific little nitpicky detail?
Well, I would probably have to say cosmology if I'm allowed to say that. But beyond that, yeah, I think if I wasn't doing cosmology, then I've also always been interested in quantum mechanics. So maybe I would have gone down that road instead. But yeah, I made that choice quite a long time ago now. So I enjoy teaching quantum mechanics at the sort of more basic levels, and special relativity as well. But I'm certainly not an expert in this field. So yeah, but that from a teaching perspective, probably quantum mechanics.
Great, that's great. If we slightly segue into teaching, as you have already, what do you enjoy most about teaching? What's the best part of it?
Trying to convey the interesting things about the course. I think so. Trying to get that message across, and it's fantastic teaching students who are obviously enthusiastic about physics. They're doing a degree, so it's just great. It's a great feeling being able to share that enthusiasm and to teach that subject. And and in some cases it's the first time that they may have learned something that that they didn't know about, and just that being able to share that and teach that is the most exciting thing, I think, the most interesting thing.
That's great to hear. Right, so for people who are considering whether or not cosmology might be something that they want to look at, whether it's just to learn more about or possibly do the same as you have done, what type of things would you suggest to look into as like a beginning thing? Because there's some sort of book or a TV show or something, or a documentary.
Yeah, I mean, I think cosmology is one of those subjects where there's lots of books, at various levels, from popular science levels to textbooks, that you can learn the subject. And so I think cosmology, people will have no problems finding a good book. I wouldn't want to recommend a specific one at the moment, but I think there are lots of books on cosmology which will teach the sort of at any level the sort of interesting ideas. And I think that's one of the things I like about cosmology. It's even though you can learn cosmology at a very high level, there's lots of ideas and concepts in there that you can learn without all the knowledge of the really complicated maths that like Einstein's relativity and so on. So you can learn a lot about cosmology even before degree level. And similarly, I think there's lots of YouTube videos and movies and TV programs that explain some of these properties of our universe, the Big Bang, the expansion, why galaxies are moving apart. So lots of these basic ideas that sort of underpin cosmology.
Okay, so definitely accessible for everyone.
I think so, yeah.
That's great. Right. Then on that note, I think that's it with my questions.
Okay, thank you.
Thanks for joining me today.
Thank you. Thanks.
Thanks again for joining us for today's interview. We really hope you enjoyed it and that you will join us tomorrow when we meet Marco Gersbeck, a particle physicist. Don't forget to like and subscribe and spread the word to your friends. The hashtag is BSW21 and our social media accounts are UOM Viz Outreach.